Okay, now we have this quiz. As I've said, everybody made, everybody that I think did the homework, and I think almost everybody did, made close to 100% on it. Okay, now I give you this quiz and ask you to rearrange these. Now, in the support course, I went ahead and gave you the rule, but I didn't give you the rule here. But people seem to be using the rules correctly. What does this indicate to me? Well, as I've often seen in this class, it looks really good. Okay. Um, uh, People not only got the homework right, but they apparently did it in such a way that they remember the doggone rules. Instead of sitting there with the rules in front of them, looking at it every time you did a problem, it looks like you weaned yourself from the rules. Either that or you got a good memory and you just remembered the rules. Or maybe you just chose to memorize the rules. One way or another, you knew the rules when you came in. Okay? So 2 thumbs up. Now, the midterm. I still don't have your tests with comments on them. I'm going to get that to you by the first of the week. But unfortunately, I've got a project going on here that college needs to have done. And the people who are going to do the project didn't tell the college when they needed everything cleared out. They just all of a sudden sprung it on us a couple of weeks ago. Okay. And this is the worst thing in the college. And I've got to deal with it. And I'm sorry, but that's got me a little bit behind. Okay. Fortunately, y'all were good to me. I didn't have to put a lot of comments into your homework because you did it right. Now, I didn't go through and, add the 5 points or whatever it is if you submitted your work. And I'd like to look at that work just to see what you do, see if you're showing the steps. I think I don't see where anybody that submitted the work isn't going to get those 5 points. So I've got to go through and do that, but that doesn't take too long. I do take a couple of minutes to look at the work. Okay, now as to your performance on the midterm, and since I'm talking to you, I might as well zoom this back a little bit. Not that you necessarily want to look at my face, but there it is. If you go to the grade book, you're going to see 2 scores. I think it's test 1 and the midterm. Okay. It tells you test 1 is worth 500 points. I think the midterm's worth 1,000. And the final exam's worth 2,000. So you got that to look forward to. Okay. From what I've seen in class, I've said it before, that people tended to underperform a little bit on the midterm. Most people. Okay. Some people did quite well. But everybody who's here right now at least had a passing grade on it. Okay. Sometimes I had to stretch a little bit to assign a passing grade, and I had to take account of effort and stuff like that. And I usually don't do that on a test. And I won't do that on the final. So don't count on leniency in grading the final. Okay. But your scores, there you got test 1. And that should read major quiz, because I got another one over there for the major quiz. So I've got to manipulate things a little bit there to make it look right. Okay. But you got test 1 and you got midterm. Okay. Test 1's worth 500 points. Midterm's worth 1,000 points. So if you have the lowest possible passing score, let me look at the grade book and make sure I'm telling you right. But I believe it's 200 on the midterm and 400 on the 400 in the midterm, 200 on the major quiz. And all I've got to do is find. There it is. Yeah. Most passing total on these two would be 600. And that would typically correspond to 200. Okay. That means there's evidence of life. Okay. And that will pass you, but with a D. Okay. Now, D won't serve as a prerequisite for the second semester of this course. But it would serve as a prerequisite for statistics and a lot of other courses. Okay. But you want to do better than it. Okay. Now, total for an A would be typically 90% of this would be 450 and 85% of this would be 850. So the total would be 1,300. I'm not sure anybody has that total. There's some people that did well here, did okay here, but didn't quite come up with that total. I'm not sure. Okay. Now, some people who had a lower score here had a really good score here. Okay. So, some people did quite well. So a 1,300 total would be an A. Now, it could be 400 and 900 would total up to 1,300. So if it's total, you would look at, but you can see relatively how you did on the two. Okay. For a B total, and these are pretty much the scores that I settled on. And I should have looked at this. I thought I had it all in my head, but this is the time of the year, April, when nothing sticks in my head. Hopefully you've noticed. That's a little bit. Well, no, I think that's right. Okay. Just looking. That would be a total of 800. It can't be right. This is 500. Okay. It's like I said. So that would be a total of 1025. And let me double check that. 75, 75. Okay, I think that's right. Then for C total. We'll do that easily. So probably gonna screw it up. But that'd be 120 here. No, it isn't. I'm looking at this number, it'd be 300 here and 600 here, and a total of 900. Okay. And looking at that, looking at this, and these aren't alphabetical, so you can't guess anybody's score. I'm seeing a 600. Okay, that'd be a D. I'm seeing a 900, which is a C. I'm seeing a 930, which is still a C. I'm seeing a 975, which I guess is a C. I'm seeing 1,070, which is a B. I'm seeing a 1,200, which is good, strong B. Okay. I'm seeing a 1,250, which is getting up close to the A total, but not quite. Okay. So right there are two that are in striking distance of making A's. Okay. Good enough that you're probably in pretty good shape. Now there's one where I think, yeah, there's one 1,400 total. There's one clear A. Okay. So I'm seeing a distribution from C's up to at least one A and hopefully a couple more by the time we're done. All right, well, let me zoom back. You know, I don't mind showing my face once in a while, but I hate for you to see the fog that surrounds my head this time of the year. Okay. It obscures the board and stuff like that, so there we go. Okay. So everybody have that down. I see some of you probably looking at your device and seeing what your scores are. But everybody should know where they stand. Okay. So there's some D's, mostly A's, B's, and C's. And I would say that the closer you are to 600, the harder you really want to work. Make sure you stay in the passing range. You want to get the homework done on time. You want to work very hard on it. Okay, now let's get back to the mathematics. And I will get your test back to you in PDF form with commentary. I'm sorry I haven't had a chance to do that, but backwards and forward. Okay, so let's go ahead and some of these equations. I'm going to do it fairly quickly. We did it also in the support course, but you probably don't need to go back and look at that. I don't think many people have to be looking at that anyhow. Some of you do need to do it. Okay, you want to improve your score or to keep yourself above water. So we have log base 8 of x equals 2. This translates. I'm not going to look at the formula. Okay, it just means 8 to the second equals 2 equals x. 8 to the second equals x. X equals 64. We're done. Okay, nothing to that one. Okay, now this one's a little bit more interesting. You probably haven't seen much like this, but log base 4 x squared minus 5x plus 6 equals 3. We immediately transform this. It's always base to the power equals whatever's in parentheses. So I'm actually going to write it this way. Because what we're really interested in is what's in here, and that's going to be this to this power. Well, that gives us x squared minus 5x plus 6 equals 64. And I'm not going to go through the steps of rearranging, but you subtract 64 from both sides. Why do you do this? Because it's a quadratic equation. Okay? And you don't have any way of solving this except to use the quadratic formula, or at least to put it in this form and see if you can factor it. Well, it's going to be hopeless to factor that. Okay? So you can use your calculator, calculate this. And I'd recommend that you do and plug it back in here and make sure it works. Okay. There's one I did. I'm pretty sure it doesn't work. It's pretty simple. Brain fog, whatever it is. I wasn't able to reconcile it in the last class. If you want to have a good laugh, you can look at that. Okay. Next problem. Natural log minus 5 equals 3x minus 2, so equals 5. That translates, what's a natural log? It's the base E log, right? I'll remind you, you have an LN button on your calculator that you're welcome to use. Okay. You're going to get 3x minus 5 equals E to the 5th. You can think log base E when you see LN. So it's E to the 5th equals 3x minus 5. Pattern is one you can get used to, but make sure you, I recommend that you make sure you understand how this expresses the fact that the log is the inverse to the exponential. That's where it all starts. You want to have secure knowledge, you lock it in there. Okay. And that's fairly challenging, but you can still do it. So you get 3x equals e to the 5th plus 5. So that x equals e to the 5th plus 5 over 3. Okay. Now I recommend that instead of plugging e to the 5th in and rounding it off, what you could do, you just leave it like this and then figure out how many significant figures you want, because you're going to get a whole calculator full of significant figures, right? If you round off, you're going to get something a little different than what you get if you keep it in this form. Okay. But e to the 5th, I don't know what's e to the 5th. It's 50, 140, something like that, maybe. Very approximately 140 plus 5 over 3, which would be 145 over 3, which would be 48 and a third. Very approximate. Okay. Don't take my mental calculation 48 and a third seriously either. Okay. I kind of think that's right. I checked it 2 different ways, but I have enough brain fog that I could have done that well. Okay. Make sense? Okay. 2 to the 4x minus 3 equals 100. Well, we translate that and we get 4x minus 3 equals 2, oh man, to the 100th power. So that 4x equals 2 to the 100th plus 3. So x equals 2 to the 100th plus 3 over 4. Now, the problem with 2 to the 100th is that that's a number about 30 digits long. It's a huge number. That 3 doesn't amount to a hill of beans, but you still have to do 2 to the 100th and divide by 4. Okay? Now, 2 to the 10th is a little more than 1,000. Okay? And 2 to the 100th is the 10th power of that. Okay? So you're going to have like 30 plus digits. Probably 31 digits, 30 or 31 digits, if you plug that in. And your calculator will probably give it to you in scientific notation. Because you can't write that. Okay? That depending on what software you might have something that would, but doesn't matter. That's a ridiculous number. But if you're trying to calculate the number of atoms in that table, won't be quite that big. Okay, maybe the number of atoms in this whole room. Okay. But you know, it's a number that has a meaning. All right. Or let's see. No, there aren't that many stars in the universe. But if you get into the number of atoms in the universe, it's like 86 digits long. So, okay. No, I just covered up. What's this? Okay, 10 to the x squared plus 5 equals 2,400,000. What's this? This tells us that x squared plus 5 equals the LOT log of this number. Okay, well, you can put that into your calculator. The LOT log is going to be something like 6.1, something like that. That's approximately equal to 1.1. Okay. And you can plug that back in here and see how it works. That was a pretty easy one to estimate. It's a little over 2. Oh, wait a minute. That might be 6.2. We'll do something. Probably 6.2. That's probably 1.2. I don't think it's 6.3, but you can figure it out and decide whether to make fun of it or not. Okay. Now, e to the 0.04x equals 8. Now, e to the 0.04, e to the 0.04x, and I'm going to change that x to t. Okay. I'm going to change it to a t because I want to put that in the context of compound interest. Okay, that's part of the formula for continuous compounding. Just to relate this to some of the applications. Okay. Continuous compounding at interest rate 4%. There's your 0.04. That's like e to the RT, which is your formula for the factor in compound interest. Okay. Continuously compounded. Okay, e to the 0.04t equals 8 translates to I'll put the 0.04 T on this side. It's log to the base E of 8. Which is most conveniently written as a natural log of 8. Sorry, 0.04 T then would be approximately, natural log of 8 is about, maybe it's 2.2. So the T is approximately 2.2 over 0.04. It is like 55. And that's about right. Okay. Now, what's this tell you? Well, for example, I think much for students do this, but I don't have any. You know, again, here's your grade correspondence. That'll go away, but it'll be on the video. And if anybody wants to know how to interpret their score, or if anybody wants me to give him any advanced comment on their exam, as I said a week ago, just email me and I'll tell you how you stand in the course, and whatever else you need to know. Okay. So digression aside. Right. This would be an example of how long does it take to increase $1,000, $8,000, and 4%. Of course, the word annual, their annual interest compounded continues. Okay. Well, what you write is after 2 years, you have the amount, $1,000 times e to the RT, which is $1,000 times e to the 0.04 T. And that might be hard to write. That's $1,000 times e to the 0.04 T. So pretend it right there. So we solve $1,000 times e to the 0.04 T equals $8,000. You divide both sides by $8,000, you get e to the 0.04 T equals 8. So that you have this equation, and you get T approximately equals 55. Okay. Now, just to say a little more about this, how many times do you have to double the $1,000 to get to 8,000? Well, what do you have? Just think it through. You don't have to say it. How many thousand do you have if you double 1,000? Show me with your fingers. Start with 1,000 and you double it. How many thousands do you have? Two. Okay, 2,000. 2 times 1,000 is 2,000. And you double that. How many thousand do you have? 4. And you double that. How many thousand do you have? Oh yeah, I need this and 2. Okay, yeah, you have 8. Okay, don't want that cog them to look like the fingers sticking out there, but you have 8. So that's 3 doublings. Number 8 is your doubling. Okay. I mean, you get 1, 2, 4, 8. Double, double, double. 3. Double. Okay. How long for 1 double? All this time. T double. Okay. That E to the R times T double has to equal 2, right? And this specific example, that's E to the 0.04 T equals 2. Okay. Well, you solve that. You can translate that to the logarithmic form. T equals the natural log of 2. I don't have enough room, so let's use a little bit more board space over here. You get 0.04 T is approximately 0.7. If you plug in natural log of 2, it's going to be pretty close to 0.7. Okay. I think it's 0.697. And the square, and the square root of 2 is 0.7. So, a couple of numbers that are kind of working that. So you get T approximately equals 17.5. Okay. I divide 0.04 into 7. It's like divide 4 into 7. Okay. 17 times 4 68, leaving you 2 or 4.5. Okay. So T is approximately 17.5. That's a time for 1 double. So let's just see how this works out. One doubling in 17.5 years. It doubles again in another 17.5 years. 2 doubling should be doublings, but I'm not going to. Is 35 years. Doublings would be 35 years. It would take another 17.5. That comes out 52.5 years, which isn't completely consistent with the estimate I made over here. I wouldn't have thought I'd have been that far off. Apparently I was. Because I didn't make a very accurate estimate of the natural log of age. But I had 2.2. I had 2. Yeah, I should probably could have 2.1 or something. Anyhow, this moment, does that make sense? After 17 years, your money will double. Now you got 2,000. Another 17 years it doubles. Now you got 4,000. Another 17.5 years it doubles again. You got your 8,000. And you're 120 years old. No, you're not that old yet. Okay. In 55 years, you'll be vicinity my age. Okay. And even if you're my age with brain fog, you'll probably be happy to have that money. Okay. So from your age to my age, you'd have 3 doublings at 4%. Of course, there's a lot of uncertainty about how everything's going to go over the next 55 years. Okay. You got artificial intelligence. You got turmoil in financial markets. Less turmoil than there was a couple of days ago. We'll see how that goes. All right. Now I'm not sure all this was as visible as I thought I was seeing it all, but I wasn't. I think now no, nothing's gonna fall off. Okay, thank you. There it is. Okay, now I'm tying all this in to what we've done last time with exponential functions and with finance, which might be in people's minds these days. I know it isn't so. And you get deep into finance and it gets highly mathematical. As mathematical as even something like quantum physics, okay, which is really mathematical, or general relativity, which is really, really mathematical. There are a lot of people in finance and people that are physicists. Can't get a job as a physicist, get a job that pays 10 times as much and become a financial wizard or financial analyst. Those guys make a lot of money. Not sure how that's going to play out with artificial intelligence. I think you're still going to need people to make judgments. But artificial intelligence do a lot of the other things. Still need people that know what it means. Okay. And you don't want to ask artificial intelligence how long it's going to take you to get $8,000. Okay. Or maybe you do want it to tell you, but you know enough to know when it's making it up or when it's trying to mislead you. And artificial intelligence could evolve to try to mislead you. You gotta watch. So you gotta know something. You gotta know something to know even what to ask your AI. So you got to know some mathematics. And I think you need to know more now than you would ordinarily, because you can't necessarily trust what you see in them, even though it's probably really good. You got to develop some critical thinking. Okay, well, all that aside, there are some rules that we use for logarithms that allow us to solve other types of equations and do other things. So we want to look at those rules. I'm pretty much going to use statements that I use in the support course. Right here. I'll just show you a couple of examples. They did really well with this in the support. Okay. You have your laws of exponents. Notice when you multiply a to the b by a to the c, you end up adding the exponents, right? Now, logarithms are inverse to exponents. So this tells you if you add two logarithms, the logarithm of one number and the logarithm of another, you get the logarithm of their product. Okay? So it's like you got a sum that goes to a product, but in a little different way, you have a sum here, gives you a product. Now remember the reasons for these rules for exponents, like a squared times a cubed has to be a to the fifth. 2a's multiplied by 3a's gives you 5a's. 2 plus 3 is 5. 2a's, a squared raised to the third power means 2a's times 2a's times 2a's, which is 6a's. So a to the b to the c, a to the second to the third is a to the 2 times 3, not a to the 2 plus. You want to understand that much about why the laws of exponents are what they are. You always want to be able to test it with 2's and 3's. And we go over that in some detail when we introduce this. Over here with the logs, well, here we've got raised this to this power, and the power is the product of the powers, right? Okay. If I have a product, a number times a log, I get the log of this thing to that number. See, this, but you're probably not going to understand it in detail. Now, if you're working at the A level or close to the A level in this course, it might be worth trying to understand that in detail. If you're working at the D level in this course and can understand that, that's a big deal. That means you're really pretty smart. You know, you understand some. It goes a little deeper than this course. Okay. If you're looking at an engineering major or something with equivalent mathematical demands, you probably want to try to think that through. Otherwise, spend your time on something else. Do this when you have time to think about something tough. Okay? Not that tough. Yeah. Okay, anyhow, these are the rules. So the sum of two logs is the log of the product. A multiple of a log is you take whatever you're taking the log of to a power, and it's the log of that to the power. Okay? Log of 1 is 0. That just corresponds to a to the 0 equals 1. That's fairly easy to understand, especially if you can construct the graph of the log. And since a to the negative b is 1 over b, dividing by b means you're going to subtract the log of b. When you do log of a over b, then you get log of a minus log of b. These things are related to these. They're totally equivalent of, there are ways to even write out the equivalents, but just make sure you can use these. They're not hard to use. Okay, so if we look at the log of x plus 3 plus the log of x minus 2, where in the rules do you see something that talks about the sum of two logs? Now look up here and see if you see it. Is there something up here that gives you the sum of, that involves a sum of two logs? You see it here, 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 or here. That'd be 1, 2, 3, and 4. Give you a minute. Is it 1, 2, 3, or 4? Okay. Some are showing me a number. Some are making rude gestures. That's okay. But yeah, it's this one. Here's a log plus a log, right? This is a log plus a log. So this thing here would be B. This thing here would be C. And what you'd have would be the log of B times C, which is a log of this times the log of this. Okay? So now you have the log of x plus 3 times x minus 2 equals 2. That makes sense? It's pretty straightforward. People did real well with it in the sport course. We understand. Okay. Well, then what do we do with that? Well, the obvious thing is use the distributive law. We get log of x squared plus x minus 6. We just multiply these two things. People are pretty good with the distributive law. Make sure you stay that way. Okay. Equals 2. And now what do we do? Well, we just translate this. This means x squared plus x minus 6 is 10 to the second power. And you know how to do that. You did that for homework almost 100% right. Everybody seemed to be doing it right today without even having to look at the rules. Okay? So you seem to be in really good shape on that. So translating this to this, I think you're good there. Well, 10 squared is 100. We put this into the standard form of a quadratic and use the quadratic formula. This is the one you can laugh at me on because I did something wrong here. And I can't find it because it's all very simple. Okay. So you want to feel superior to me. See if you can solve it. The reason I say this is negative 11 doesn't work worth a darn here. And 10 doesn't work all that well, but it does kind of work. Okay. Because a log of 10 is 1. And that's a little more than 1. That's a little less than 1. That gives you 2. But negative 11 doesn't seem to work. Now, what's wrong? Well, actually, I'll tell you what's wrong. It's not that I made a mistake. It's that you can't take the log of a negative number. Negative 11 will give you negatives under here, and you can't do the log of a negative. Okay? If you sketch the graph of the exponential function, logarithmic function, and you've actually done this so you understand why this is the inverse of this, just by reversing the x and y coordinates, you see that x, negative x, doesn't correspond to anything on the long term, right? Negative x, negative values of your number on this axis are not in the domain of the logarithm. The domain of the logarithm function is all positive numbers, not even 0. Okay, just positive numbers. And you can see why if you understand the construction of the graph of the log function, which you do. You've been doing that since the first day. Okay. And then how you construct the logarithm function. So construct the exponential, reverse the coordinates, sketch the log. Very easy. Okay. Make sure you know that. It will likely come in handy someplace on the exam. I might even ask you to construct it and make an estimate. Not hard to do. Again, you know how to construct the logarithmic shape, put numbers on it, reverse the coordinates, and sketch that. Okay. Okay, well, that is an illustration of this rule. And these rules usually don't give people much trouble. Okay. They're explained well with example and open math and stuff. And I don't think it's any harder than what you did for homework last night or whatever you got around to do. Some people did it early too. I don't know what's the matter with some people. You're supposed to wait to the last minute. Okay, get on the ball. Seriously, when I looked yesterday afternoon, a lot of people were done with it. Okay. And then when I look today, I think everybody did well. Okay. Keep doing that stuff. Let's take this equation. This is a log 2. Now, this applies no matter what the base, as long as the base is the same for both. Okay. So we have this equation. We can't apply this rule because this rule doesn't allow for a number in front of the log. Okay, notice we have a 2 in front of this log. So you can't use this rule. What you can do though, if you have a 2 in front of the log, well, you can use this. This allows a number in front of a log. Okay, so if you got a 2 in front of the log, 2 times the log of whatever is that whatever raised to the second log of that whatever raised to the second power. So we can write 2 log base 2 of x is a log base 2 of x squared. Look at that for a minute, make sure you've got it digested. I'm going to explain it again. Cross your eyes, beat your head on the table. Raise your hand, whatever it takes to let me know you don't understand. Okay, I'll explain it again. Everybody okay with that? You see how this rule allows you to take this and write this. Okay. Now we have a log and a log with no numbers in front of it. We can apply the first rule. So we have the log of this times this, log of x squared times x plus 4. And it's still equal to 4. It's still log base 2. And then we're kind of home free. Okay, except this leads to something that was kind of interesting, so we did it. We translate this to exponential form. We get 2 to the 4th is equal to whatever's in here, which is x squared times x plus 4. Okay. And then we get a polynomial. We multiply x squared by x plus 4. We get x cubed plus 4x equals 16. Okay. Now, how do we solve that equation? Well, first, we put it in the equal to 0. 0 property of multiplications, the terminology you see, and we've used again and again, and we're going to use it here. Okay. Well, I looked at this and I said, yeah, it's unlikely that we're going to find just by trial and error. And I didn't make this up. I just put down expressions and put a couple of 4s in there, which shouldn't tempt you off, and 2. Okay, that was going to be possible. But I look at this and say, we're probably not going to find a number that makes this equal to 0 by trial and error. Okay, but we're going to use factors of 16, which are 1, 2, 4, and 8, and 16, and plug some of those numbers in. So I looked at it for a minute and said, well, let's try 2. That's not going to work, but let's see. 2 cubed is 8. 4 times 2 is 8. 8 and 8 minus 16 is 16 minus 16, which is 0. Duh. So now I know the 2 is a root. Now, I didn't plan for this thing to be easily solvable, but it turns out that it is. So what do I do? Now, this is kind of review, but something you should remember because we've done it recently. And if it jogs your memory, so much the better. Think about it, because you could end up having to do something like this. Okay, so 2 is a root, so we divide x minus 2 into x cubed plus 4x minus 16. Okay, well, you know how to do long division. Now, a lot of you went to synthetic division. Remember, I will ask you specifically on some questions to use long division because that tells you what you're doing. Synthetic division is a trick based on long division that doesn't tell you much, except it's very convenient to get a quick answer. Okay, and most of you probably used synthetic division because when I looked at the work you were submitting, I saw a lot of synthetic division. And of course, open math tells you use synthetic division. I disagree with them. I think you need to know long division because you can forget the rules for synthetic division. Long division is something that's actually easier long-term to remember. Okay, synthetic division is just a trick. It's a great trick. It's a great algorithm. But I want you to know what it's based on, which is long division. Anyhow, we did the long division, and I kept screwing it up. I kept seeing this 4 here and wanted to put a 4x here instead of a 2x. And it took me a while to figure that out. Again, you could see the brain fog rolling off my head. Okay? Except I was smart enough to try to keep my head out of the picture. Okay. Anyhow, there it is. There are the details. It's very simple. And we get x squared plus 2x plus 8. So now we've factored this. We've got x minus 2 times x squared plus 2x plus 8 equals 0. Right? Because this equals this times this. We should know that about long division. So now we set this equal to 0 here, because if this is 0, the whole product is 0. And then we set this equal to 0, because the whole product is 0. Okay, if this is 0, everything is 0. Well, this has an easy solution, x equals 2, and this is easy to solve, it doesn't exist. And if you plug the numbers into the quadratic formula, you'll see why. You just check your b squared minus 4ac. 4ac is going to be 4 times 1 times 8, and that's going to be subtracted. That's subtract 32 from 2 squared. It's going to end up 4 minus 32, negative 28. It's clear that it's going to be negative. This number is too small compared to the product of these two numbers. Think about it like that. But of course, it doesn't take long just to write out the discriminant and see that it's negative and you don't get a solution. Okay? And if you're in a hurry, that's a good first step. Make sure your discriminant is not negative. Save yourself a little writing. But it's not that much writing. Got to write the whole thing out. That's fine. As long as you do your arithmetic right, you'll know that that has no solution. Well, now what does that tell us about the graph? Because I'm trying to figure out where this thing equals 16. Well, we might have another number over here other than 16, in which case, well, it's not going to apply. In any case, we've got enough information here to at least attempt a graph of this function. What do we know? We know that if x equals 0, we get negative 16. So we got y equals negative 16. There's the y-intercept of the graph of y equals x cubed plus 4x minus 16. Okay? And we know that when x equals 2, it's 0. So here's x equals 2. There's your x-intercept. We know it goes up this way. We know it goes down this way. At least if you know how to test for the long run behavior, the end behavior, whatever the open math video you happen to be looking at says. I'll say it both ways. So we're covered. Okay. We have this. Okay. If we want to know when this is less than 4, maybe that occurs when this is less than 0. We could solve this inequality. We could solve x cubed plus 4x minus 16 less than 0 very easily. We know that's going to occur to the left of x equals 2 because the graph only has 1, 0, and it has a negative y-intercept, right? The graph has to look something like this. Now it's going to have some wiggles somewhere, but they're not going to be such that it goes through the x-axis more than once. So we know if x is less than 2, this polynomial is negative, and that might tell us something about something else that we want to know. All right. Okay, so these rules are really easy, I think, to apply with practice, and the homework is going to give you several of these. Okay, now there's one more thing we want to look at that recorded, and that was also good. Okay, so again, we've got these two equations. Okay, now what we do is something that's familiar. We'll sketch the graphs of the two equations using intercepts. We let y equals 0, see that x, this equation would be 3. We let x equals 0, we see that y equals 2. So here are the intercepts for the first graph. We do the same thing for the second graph. And you can verify the intercepts. The graphs cross at this point for y equals 1.3 and x equals 1.5, according to the estimate based on this not very accurate graph. If we plug x equals 1.5 and y equals 1.3 in here, we get, I think, this side would be 13.8, which is kind of close to 12, but not all that close. This side, I think, is about 8.1, which is kind of close to 6, but not all that. Now, we want to find out what the exact values of x and y are that make these two equations come out exactly perfect. Exactly right. So what I do is I take -2 times the first equation, meaning I multiply both sides by -2. That gives me -8x minus 12y equals -24. Then I just write down the second equation, which is 8x minus 3y equals 6. Oh my God, look at how that works out. No, never mind, doesn't work out that good. It actually works out pretty close. It's nothing. If I add 8x and -8x, I get 0. If I add -12y, -3y, I get -15y, and I get -18. Okay, luckily I didn't get what I thought I was supposed to. And we get y then equals -18 over -15, which is 1.2. Now, how does that compare with my estimate, 1.3? So far, I'm doing pretty good. Okay. Now, how do we find x? Well, we take this y equals 1.2 and we plug it in for y in either equation. If we plug it into the first equation, we get the equation 4x plus 6, and I'll put my 1.2 in here. Blue indicates my y value in this case. Okay. That should equal 12. Well, that's 4x equals, now 6 times 1.2 is 7.2. That would be then 4.8. And x equals, oh, it's deadly 1.2. How about that? So my x equals 1.5 is a little high. Okay. Now, if y equals 1.2 and x equals 1.2, let's see if this works. We've got 4.8 and 7.2. That adds up to 12. Now, that's not surprising because I plugged this number into the first equation. So whatever this number is, if I did this right, it's going to work in the first equation. Doesn't mean it's going to work in the second equation. We've got to check that out. I'm keeping my fingers crossed. Okay, 8 times 1.2 is 9.6. 3 times 1.2 is 3.6. 9.6 minus 3.6 is 6. Now, ordinarily, I go ahead and write these up. We've actually done this before. Some kind of refreshing your memory. Okay. Now, for, I think for Monday night, you have some problems with systems of two equations. So I wanted to prime you for that. Okay. I think you're going to do okay with that because we've done something similar previously. And this example ought to give you a good start. You can graph the things and estimate a solution. And see, I wasn't that far off. I should have had 1.2 here and 1.2 here. It wasn't that far off with 1.3 and 1.5. But when I plugged in 1.3 and 1.5, I didn't get all that close to 12. And I didn't get all that close to 6. Okay. So by being off by just a couple of tenths on each of those numbers, it didn't check out real well. But then when I did the solution, I got something that worked just fine. Okay, so there it is. And we're a minute over. I apologize. But go do some more good work and let me know if you have questions, okay?